streaming is starting right now. So I should see confirmation that streaming is up and running in a few seconds. Yep, there we go. Alright, cool. I can now close this window and turn off the lock. Turn on the lock, I should say, in OBS. Get back to Discord. Get back to the browser. And we are ready to go. We got 20 seconds to spare. So I'm hoping all of you got a chance to read the trace of Dijkstra's algorithm. And today we're going to move on to the A-star algorithm, which is kind of fun. All right, so it is time to get started. I am going to see if there are any questions about Dijkstra's algorithm and the trace that we did on Monday. Because if there are any questions about that trace or about the algorithm itself, let me kind of scroll back to the algorithm first. This is Dijkstra's algorithm. It's a pretty textbook kind of algorithm. There are different types of implementation. Some literature would use a stack instead of a set to represent a queue. Some algorithms start with only one single vertex, and it can only designate one destination vertex. And the one that we are dealing with can deal with multiple destination vertices, and when the algorithm completes, it would have found the shortest paths from every single vertex to its shortest destination. So that's Dijkstra's algorithm. I'm not seeing any questions in the text channel, so go ahead. Somebody has the voice channel on? Nope, maybe not. Alrighty. So if there are no questions, we're going to move on to the A-star algorithm. So the A-star algorithm, it was intended as an improvement on Dijkstra's algorithm by the incorporation of a heuristic function. So the heuristic function is kind of interesting. If you kind of imagine that you are looking for the shortest path from a certain point to, for exam 2, where we're supposed to, I sent it by email. Unfortunately, for whatever strange reason, it all got rejected. So Jonathan W. was asking about the details of the score for exam 2. I did run the script. The script ran as before. Unfortunately, all the emails bounced back to me, saying the recipient could not receive the email. I do not yet know why, but I will try to figure out a way so that you guys can know the details of why you got the score that you got. Yeah, it's really kind of odd. I think District is doing something because the script has not changed. I have been using the same script for at least 2 to 3 semesters. And every semester, even with a large class in CISP440, I would be able to send email to every single student, that contains all the details of how the points or the score breaks down. Unfortunately, this semester they did something so that in CISP440, which is a larger class, I could not even send email to all the students. The API comes back and say that I have used up all the allowances for the day, basically. So something has changed, okay, and I'm gonna have to figure out why that is the case. Canvas, on the other hand, is very limited in terms of what I can import. So I can import a single score, but I cannot import comments, which is a requested feature, I think, since 2017, and it has not been implemented yet. I think some people have done something with Temper Monkey, okay, which is an add-on to a browser, to do something similar, but I'm not really sure, whether that's a good idea or not. So lots of technical difficulties, this semester because something was changed from at the district level. So I will try my best, Jonathan, to get those details to you guys. But if you're concerned about yours, I can always just kind of isolate and send you the one that you have. Of course, if the entire class asks for that, that's going to be a lot of emails. So I'll look into a solution to that problem. All right, so back to Dijkstra's algorithm. Are there any questions about Dijkstra's algorithm? Okay, I'm not seeing any comments in the text channel, so that means I'm going to move on to the A-star algorithm. So the A-star algorithm is actually, it's nostalgic to me. It's nostalgic because my dissertation, that's a long time ago. I finished my dissertation in 1995, and that's before a lot of you were born. So anyway, I finished my dissertation, and my dissertation was actually based on the A-star algorithm, except the transitions was assumed to be probabilistic. And as it turns out, most of the algorithms and all we know about the solution is no longer useful, when the transitions are not deterministic. So, so that's why, the A-star algorithm is kind of nostalgic to me. You can still take up my dissertation if you ever go to UC Davis. You can go to the physical science library if it is still there, because they might have built something on top, or I don't know. I mean, probably a lot of changes have happened since then. Oh, it's still there. Okay, so you can look up my dissertation. I believe you can just look up my name, and then it will be able to locate my dissertation, because they keep a physical copy of all the dissertations. This is before they turn everything in digital form, so that they can actually just push everything onto the web. So I'm not really sure. I don't think so. I don't think they have done anything to digitize the older dissertations, because for the most part, I mean, really, a lot of dissertations are just something that's useful at the time in order for a graduate student to graduate, and then after that, most dissertations become useless. So anyway, let's get back to the A-star algorithm. So the A-star algorithm attempts to solve exactly the same problem as Dijkstra's algorithm. In other words, you're given a graph. Okay, so let me switch to Joplin. So you're basically given a graph exactly like what we had on Monday. You have a bunch of vertices. You have a bunch of distances between of edges. So distance is applicable only to edges, single edges. And your job is to find out what is the shortest path to go from a single vertex to a single destination. So this part, with the A-star algorithm, you do have to designate a single starting point, and you can only designate one single destination. So there we go. I believe that you might be able to easily extend the algorithm to handle multiple destinations by having transitions or having edges of a zero cost, so that all the destinations will have a zero cost edge to go to a virtual destination, which is what the algorithm is trying to solve for. So there might be easy ways to extend that functionality, but the starting point, there's not a whole lot you can do. You can only start with one single vertex. You cannot say I want to find the shortest path of all of the vertices. That doesn't work with the A-star algorithm. So I'm using exactly the same graph that we did on Monday. But in addition to the graph, which has a set of vertices as well as a set of edges as well as a function d to map all the edges to the distances, now we have one extra thing, which is called the heuristic. So the heuristic is a function, and as a function, what it does is it will map a particular vertex. Well, actually, it maps the way I'm representing it here is very specific. It is not general. So in the most general form, the heuristic will take the Cartesian product of vertices and map a tuple of two vertices to a numerical value, which is the guesstimate, okay? Which is the guesstimate of the length of the shortest path between those two vertices. So the way I have it depicted here is actually much more specific than it really ought to be. So let me just kind of change the representation so it is actually correct. So it is taking, this is the estimate of the length of the shortest path from E to E, and this one is from D to E. So everything is to vertex E because vertex E is our designated destination vertex here. So I'm going to change all of these here to use a two tuple instead of a single vertex, because technically speaking they are two tuples to specify from which vertex to which vertex. Alright, so there's a little bit of text traffic. It's kind of like L, except generally speaking, you can say you can basically try to specify the H value between any two vertices. So not how should I put it? Out of the two vertices, you do not require one to be a destination. But when we practically apply the heuristic function, what we want to do is to figure out, a guesstimate, a easy to compute guesstimate between a vertex and the destination, because in this case we only have one single destination. All right. Oh, thank you, Aman, because that can come in handy. Because now you can open it up on a separate window, and then you can keep it on your desktop somewhere. Depending on your screen resolution, sometimes it's easier, and sometimes you can still have overlapping windows, which is kind of problematic. All right, so the next question is, so what are there any restrictions for this particular function h, other than the domain is consisting of the Cartesian product of or a subset of the Cartesian product of vertices, and then the codomain is going to be the set of non-negative real numbers. Alright, so I'm not seeing any questions. So out of all of these values, all of these h values, all of the heuristic values, the ones that are really useful to us would be the ones where the second item of the two tuple, in this case those are the e's, so E, 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 and E. So only these are useful to us, in the application of the A star algorithm. There's one more restriction. The one additional restriction is this particular guesstimate cannot be overestimating the actual length of the shortest path. That's the only restriction. So are we understanding what that particular statement means? The heuristic values, cannot overestimate the length of the shortest path between the two vertices that we are trying to represent. In other words, I'll pick one example here. This CE0, the third entry over here, basically the length of the shortest path between C and E has to be greater than or equal to 0, which in this case is fine because the shortest path from C to E is 6, and 6 is greater than or equal to 0, so it has met that requirement. But it would not be okay if this entry had a value of 7, because 7 is greater than the length of the shortest path. So it's good. Several people are typing, which means we got questions, and questions they're good. They're good signs. All right, so I'm still a bit confused about how the values are generated. They're not exactly generated, so typically there is a systematic way to figure out the heuristic value without actually having to find the length of the shortest path, because that's kind of the idea, right? Because if you already know how to find the length of the shortest path, then we don't need a heuristic. So the heuristic is basically a very easy way to compute something that cannot be overestimating the length of the shortest path. It's not a paradox. It is not a paradox. I can give you guys an example. Okay, so in order to give you that example, let me see if I can go to Google Maps. All right. Excellent. So here we have Google Maps, and we want to basically set a origin, where we start, and also specify a destination, which is where we want to be. So for no particular reason, I am going to say that alright, so for no particular reason, I want to go from, okay, it's easier to specify a intersection. So I want to specify here, this intersection over here, which is between Highway 80 and, what is that? Orangeville, which is the street. So I'm trying to figure out, what is the quickest way to go from here to the airport. Okay, so that's what I want to figure out. So the airport is now the destination, and the heuristic function is something that we can quickly compute, but it has to be something that cannot be overestimating the actual length of the shortest path. So if I were to go from here to here, obviously, the straight line approach is not going to work because we do not have a single highway to go straight between these 2 points. Instead, we probably want to get onto Highway 80, and then Highway 80 merges or turns into, or you can get onto Highway 5 northbound, and then from Highway 5 northbound, then you can get to the airport. Okay, so what does this have anything to do with the heuristic function? So the heuristic function in this case can simply be using the straight line distance between any 2 points. It cannot overestimate. Yes, so Armand, you're correct. It cannot overestimate. It can underestimate. It can be exact, but it cannot be over. And that's the only one restriction that you cannot that's the only restriction in order for the A-star algorithm to work. Why not be 0? Yes, it can be 0 for everything. Except in that case, if you turn all the heuristic values into 0, then you basically just turn the entire algorithm back to Dijkstra's algorithm. So let me explain why Dijkstra's algorithm is not going to be helpful in this case. Alright, so to do that, yes, A-star is particularly greedy. we have been talking about greedy algorithms, and A-star is particularly greedy because it has the use of a heuristic function. So let me just kind of try to explain, what that means, okay? Because what does it mean if it's extra greedy? So, all right. So let's get back to the problem that we have here. So what I need to do is I am going to take a screenshot first. So, I do not have the screenshot shortcut key set up here, so I'm going to have to go through the long way to get to my screenshot. Alright, so we want to select a region, capture the mouse pointer. Nope, you don't need to do that. Alright. And I want to expand it a little bit, include more area on the other side. Alright, so here I have my screenshot, put it into the clipboard, and then I will open up Zerno, which allows me to actually doodle, and it's going to be handy in this case. Question is, where did it put it? Okay. There we go. Okay. Alright, so here's Zerno, which allows me to use my stylus to draw stuff. And here's the right screen size. Alright, so paste. Excellent. That works. Alright. Sometimes I am amazed that technology actually works. Alright. So now I'm going to have to draw something on the screen. Alright, so this is where we want to be, and X marks the spot, okay? And this is where we start. This is the intersection that where we start. In other words, we are at the intersection between Orangeville, the street, and is that the street? I'm not sure. That could be Greenback. Nope. All right, doesn't matter. Okay, this is where we are starting. So with Dijkstra's algorithm, okay, Dijkstra's algorithm, the one that we have, is starting with the destination, which is over here, and then what it does is it expands the boundary, in concentric, almost concentric, circles, and it keeps expanding and expanding until we get to the point or the vertex that we want to get to. Now, when you're using Dijkstra's algorithm in CISP440, instead of starting from the destination, we'll be starting from the point of origin. So let me see if I can do this. Okay, I'm going to change my color to orange. There we go. Yellow. All right. So with Dijkstra's algorithm, which does not have the use of a heuristic function, and assuming we're using the one that is the original one where you can only have one starting point and one destination, then it's going to start the algorithm at the starting point. So the way it works is it kind of expands in a concentric way, like this, and it keeps expanding it until we get to the destination. And then you can say, oh, okay, now that we get to the destination, and there's no likelihood that we can find a shorter path, we can stop the algorithm. That's basically, an uninformed search. Okay, but you can see how this is not really that intelligent, right? Why would I? Okay, let me change to a different color here. Why would I start here and go backwards? Okay, there's no way that going back to Folsom from this particular intersection would find me a faster way to get to the airport. Okay, that it just doesn't make sense, right? So, but if you use Dijkstra's algorithm, that's what it's going to do. It will keep expanding from the point of origin, where you start with, and it will keep expanding, the vertices to explore until it has explored the destination vertex itself. And on top of that, okay, we also have to make sure that the first path that we have to the destination, or whatever path is currently in store, is not guaranteed. As long as it is not guaranteed to be the shortest one, then we'll keep expanding until we are sure that it is the shortest one. And that's going to be making use of what is equivalent to the L function, because we can basically say, okay, this is the shortest one that we have found so far, but so if all the other paths are longer than the one that we have found so far, then we have a conclusion to say that, okay, we cannot possibly find a shorter one. So that's sort of how the original Dijkstra's algorithm works. But this is also exactly what's going to happen when your heuristic function is a 0. So if you just want to say, oh, of all the functions that I can use, the easiest one to compute and guarantee not to overestimate, the distance between two vertices would be a constant of 0. That makes sense, right? It's very easy to compute. But then what you're doing is you are degenerating A star algorithm back into Dijkstra's algorithm. In other words, you'll be starting from the center, the origin of where you start, and then you'll be expanding, outward from that until you get to the destination. So I'm going to try to use my mouse pointer to point, because my stylus doesn't really have a visible pointer. So we start from here, and then we just keep expanding in a concentric way. Now, it's not exactly concentric, but conceptually it is sort of like concentric. It expands in all directions until we get to the destination. And you can probably see in this particular way, if I keep expanding, it's going to be getting to probably El Dorado Hills. Okay, and it makes no sense that we have to explore all the streets, all the intersections, all the way around this point of origin and all the way to El Dorado Hill on one side, and all the way down to Elk Grove on the other side, and so on and so forth. Does that make sense so far? So you can make the heuristic function just 0, But in that case, you're degenerating A star algorithm into a uninformed search algorithm, which is Dijkstra's algorithm. Cool. Okay. So what is the difference? What kind of heuristic function should we use? So the heuristic function that we can use in this case is simply to look at the straight line distance. So the heuristic function for this particular vertex versus the destination would be just the straight line. So let me see if I can actually draw a straight line with this tool. I don't think so. Those are erasers. Oh, I can draw lines. Cool. Who would have guessed? So that means the distance of this line would be an estimate. This can be used as the heuristic function to estimate the actual distance between the intersection where we start to the destination where we want to go to, because there's no way we can go on this straight line. So this straight line is guaranteed not to overestimate the actual distance. Alright, so there's a question in the text channel. Are the heuristic value kind of like the infimum maximum lower bound? Not exactly. Not exactly, because we are not talking about a sequence of numbers. We're talking about a single number. So we need a single number between any vertex to the destination vertex, and that number just has to be not overestimating. That's all. Yeah, so it just cannot be overestimating. It can underestimate by a good margin, okay, but it just cannot be overestimating. Alrighty. So is everybody else understanding this concept? Okay, I can give you. So from this perspective, the actual function, the actual heuristic function, is very easy to compute. Let's say we are dealing with this point here, then all we have to do is to figure out the distance of that line. If we are what is nice about this is, if when we start to estimate from or when we try to consider vertices in the opposite direction, guess what? They're all going to have, let's say we're talking about this intersection over here. Guess what? This line is going to be longer than the other lines, which are more along in the direction that we want to go. So by using these heuristic function to estimate, what is to basically underestimate, even though they can be exact, but most of the time they're underestimating. So when I use the term underestimating, that is simply me saying it is not overestimating. Is that okay? Does everybody kind of understand the potential fallacy of what I just said? Because most textbooks will refer to a heuristic function as an underestimate of the distance of the length of the shortest path between two vertices. But that is not entirely true, because they can be exact, can be exactly the same. So we really should not be using the term underestimating, not underestimating. Well, I should say we should not be using the term underestimating. We should be using the term not overestimating. Yes, exactly, less than or equal to, instead of just less than. So this is why it makes sense, okay? This is why it is useful, because when we add, okay, so when we add, okay, let me pick a different color, let's say green. So when we add the distance that we already know going from the origin, which is this point over here, to this point over here, and we just add the heuristic function from this point all the way to the destination, these two lines, the green line and this blue line combined, is going to be pretty long. As opposed to, okay, so as opposed to, we figure out how to get to, okay, let me pick yet a different color. This time we will pick orange. So let's just say that we have somehow figure out, okay, it needs to be in segments. So let's say this is the exact path that we know how to get to this point over here. So when you add the length of the orange line, which is exact, to the length of this particular blue line, which is an estimate, that combined length is going to be less than this green line combined with this particular blue line. Does that make sense? And as a result, the algorithm will basically automatically try to only explore vertices that are kind of in this direction, and vertices in the opposite direction, it will basically stop exploring those really soon. All right, so Jonathan's getting it. All right, sort of like it's more like a priority kind of thing. It's basically saying, oh, if you head up in that direction, it is very unlikely, or it would be, it's very unlikely that you can find a shorter path. But that's based on how we use, what we use as the heuristic function. So if we use, the straight line distance, which are the blue lines in this particular map, as the heuristic function, then we have that clue that we might be heading in the wrong direction. On the other hand, if you use a heuristic function of just 0, then you are just as uninformed as in the usual Dijkstra's algorithm, which means you're going to expand the concentric circles like the yellow circles until the circle encompasses the destination, which means you're going to have to explore a lot more vertices than the approach of using A star algorithm, using a nice and intelligent heuristic function. All right, a better starting point to base where we should look. Right, it sort of points you to the quote-unquote right direction. Alrighty. So now the question is, instead of giving, so if you want to trick A star algorithm, okay, the A star algorithm, instead of giving the A star algorithm a smart heuristic function like the blue lines that we have on this map, what if you want to trick it? What if you just give it some totally crazy heuristic where when you go in the opposite direction, the heuristic function would actually be 0, but when you're heading in the right direction, it'll be the exact length of the shortest path of the vertices to the destination. In other words, you're giving the heuristic, you're giving the A star algorithm the worst possible advice in the form of the heuristic. The question is, would that break the algorithm? And the answer is, well, we certainly hope not, right? Because otherwise this algorithm is not even worth discussing in class. So the answer is no. As long as the heuristic is not overestimating, as long as that rule is observed, the A star algorithm will always find the shortest path. You can try to trick it, and as the result or the consequence of tricking it, the A star algorithm may need to explore a few more vertices, but it will always find the shortest path. All right. So do we have any questions at this point about what the heuristic function is, and generally speaking, how it is going to help in improving the efficiency of finding the shortest path? Okay, I don't see any questions. Maybe people are still thinking, so I'll let you guys think a little bit more. All right, Wade is typing something, so we'll go ahead and wait for that. You can use the voice channel if you wanted to. So, could we summarize in plain English one more, like no examples? Sure thing, absolutely, because that's what my web page actually has. So right here, the heuristic function has to be admissible. That means if L, V, X, V, basically the Cartesian product of V and V itself maps to non-negative real numbers, represent the actual length of the shortest path between two vertices, then for all VW in V, the uppercase V, which is the set of all vertices, H of VW has to be less than or equal to L of VW. And that's it. I mean, that kind of captures the restriction of what we need the heuristic function to play by. Yep. But the example is useful in the sense that it tells you why in most cases, hopefully we can find a good heuristic function, and it is going to be useful. Because if you look at the example, let me switch back to Zerno. So when you look at this particular heuristic function, it's very easy to compute as long as you know the actual coordinate of these intersections. The distance between that point and your destination, it doesn't take a whole lot of time to compute. So as a result, this is a very useful heuristic function if navigating on a map is what we want to do. All right, so getting back to the notes here. So in the application of the A-star algorithm or the Dijkstra's algorithm to solve for the shortest path between certain vertices, a lot of optimization problems can be casted as the problem of finding the shortest path. So that means for each individual application of the A-star algorithm, we probably have to think about what makes sense as a heuristic function. And it is not my job, in this particular module, to give you a universal solution of this is how we figure out the heuristic function. So I cannot tell you that because it really depends on the nature of the graph. Okay, what you are representing as vertices, what you're representing as the edges, and also what kind of distance are we talking about? Because you can talk about distance, quote unquote distance, in just using driving as an example. It can be how much gas you're using. It can be how much time it's going to take. It can be how dangerous is a particular route. Okay, basically from the perspective of insurance claims and so on. So it depends on what the edges are really representing. That sometimes we may figure out some heuristic function that's easy to compute, and other times it may not be so easy to figure out a heuristic to use. All right, so the next paragraph here talks about something that we just talked about. We can define h of vw to be just 0 for every way to combine v and w. In other words, the heuristic function is not informing you of anything. Okay, it's basically useless. So in that case, you are degenerating the A-star algorithm into Dijkstra's algorithm. Now, worse things can happen. Okay, you would think an uninformed heuristic is bad, but you can actually turn the heuristic into something that is that gives you the wrong information as much as possible. So it will actually send you try to explore in the opposite direction before heading into the right direction again. But we'll see that the A-star algorithm cannot be tricked to the point where it will give you the wrong solution as long as the heuristic is admissible. The term admissible simply means that the heuristic function cannot overestimate the actual length of the shortest path between two vertices. So are we good so far? Are we getting a understanding of what the heuristic function is, and also what role it is going to play in the A-star algorithm? All right. Oh yeah, we are going to do a walkthrough, but before we do a walkthrough, I'm going to explain the terms first, okay? Because otherwise, we'll be dealing with the logic of the algorithm while introducing the terms at the same time. So this is what I'm trying to do is to introduce the terms. So we have introduced L, which is basically the same as the L function from the from Dijkstra's algorithm, except this one is more general because it is the length of the shortest path between any two vertices. But in reality, we only really care about the length of the shortest path from a vertex to the destination vertex in this case. But there are two more terms that are useful here. One is called the g function, and one is called the f function in this case when we are talking about the A-star algorithm. So now we're getting into the algorithm, and the first thing is, what are we given with? Okay, so we are given with all of these things here. So we are given with everything that I have highlighted here. So we're going to explore this rather quickly because some of these are very, very obvious. So we're given the graph, okay? That's kind of obvious. Without a graph, how are we supposed to figure out, the shortest length, the length of the shortest path between, the starting point and the destination vertices. And the graph is represented by a set of vertices and a set of edges, okay? Nothing new here. We are also given with a function d, which is telling us the distance between the distance of an edge. Okay, each item is giving you the distance of a edge, of an edge. So that's new. That's not new neither, because we have been using the d function in Dijkstra's algorithm as well. In Dijkstra's algorithm, or at least my variant of Dijkstra's algorithm, we have a set of start vertices. In this case, because we're dealing with the A star algorithm, we can only have one single start vertex. So we only have one single start vertex, and it is designated as S in this case. It is an element of V, obviously, because it has to be one of the vertices. And then we're also designating X as our destination vertex, because guess what? X marks the spot. So that's why I use X to represent the destination vertex. So once again, this is also not different from Dijkstra's algorithm that we talked about earlier on Monday, because in Dijkstra's algorithm we have a set of destinations, and for the starting point we do not have a particular starting point, because it will solve for the shortest paths between any starting point and the closest destination. And then on top of that, we also have h, which is our heuristic function. So technically speaking, the h function is xv, which means it's mapping, it's telling you a not overestimate distance between any two vertices. But in reality, we only care about the heuristic function from a vertex to x in this case. So all of the other items in this particular function, they're not utilized in any way at all. So those are all the givens. So now we're actually starting to look into the algorithm itself. But before we start on the algorithm itself, let me see if there are any questions about what A star needs to be given with. We got V, the set of all the vertices. We got E, the set of all the edges. We got D, which is a function that map an edge to the cost of the edge itself. We have lowercase s, which is a single start vertex. We have lowercase x, which is a destination vertex. And then we have h, which is a heuristic function. So even though h is supposed to be a pretty large function to give you the non-overestimate of the length of the shortest path between any two vertices, the one part that we would actually use in h would be just the non-overestimating estimate between a vertex and the destination vertex. So those are the things that we are starting with. That means non-negative real numbers. So this little notation here is just how I designate as non-negative real numbers. So it can include 0, but it just cannot go negative. All right. So I'm just checking to make sure that we don't have any questions about what is given to us before we proceed. All right, so we got some text traffic going on. Alrighty. I was confused because I thought we were discussing a specific heuristic. Now, the heuristic function just has to be a function, and it has to be admissible, and those are the only assumptions that we need to make in order for the algorithm to work. So h is just some kind of function that has to play by the rules of being admissible. All right. Alright, so doesn't look like we have any further questions. If anyone needs more time, just let me know. and I can certainly check to see if there are any direct messages. Nope, no direct messages. So just let me know if you need more time. Otherwise, we'll move on to talk about the initialization of two functions. One is called g and the other one is called f. Okay. Doesn't look like we have any questions at this point. All right. So now we're going to go through the initialization, and there are two functions that we have to initialize. Function g is the actual length of the shortest known path from the start vertex to v. Okay, so this is not going to the destination. This is going to a particular vertex v. And then f of v is the estimate of the length of the shortest path from the start vertex through vertex v to x. Okay, so right away we're going like, I have no idea what this means. Okay, well, I mean, because it is kind of abstract. So to understand this part, I'm going to go back to Zerno, because this is the best way to illustrate it. And this time I'm going to use my stylus to actually, I don't need to use the stylus because I think I can just type. So I'm going to use the text tool here. Make sure it's using a reasonable font. There we go. So see this orange line here? That is the actual path. Okay. So the length of the orange path here is okay, let me go back to my notes because sometimes I confuse myself. This is the actual length of the shortest path from the starting point to a particular vertex v. So this is g. Okay, so this is g of v, and v is basically this point over here. This is your vertex v. This is vertex x because x marks the spot, and this is vertex s because this is the starting point. So g of v is referring to the length of the orange portion of this path here. And then you might ask, so what about f of v? So f of v is a little bit harder to describe, and the best way to do it, let me see if I can do that over here. Okay, so I have to turn off to not use the text tool and doing straight line again. Okay, very good. So if you add up this portion and the orange line, that becomes f of v. So f of v has a easy way to designate it. You can actually use an equation to denote it. So f of v in this case is g of v, which is the length of the currently known shortest path from the start vertex s to a particular vertex v, plus the heuristic of going from v to x, the destination vertex. That is basically what f of v is really about. It is still it's an estimate. Okay, it is an estimate of actually I think. Yeah, so this is correct. So it is an actual estimate. It is an estimate of the path, of the length of the path from the start vertex through vertex v to the destination. Exactly. So Armand is correct in the text channel. It is the estimate, which is the heuristic function, plus the current shortest path, the length of the shortest path known at this point, from the start vertex to vertex v in this case. So why is g of v being set to infinity? Because at the very beginning of the algorithm, we haven't explored anything yet. In other words, in this case, what is labeled orange in this case, that's after the algorithm has run for a little bit already, so that we have already explored the edges along this way from S to V already, and that's how we can establish the orange line. Alright, so next we have by current shortest path known means that we have explored so far for the shortest path. So it is because the first time we get to a vertex from the start vertex, we may not have found the actual shortest path, as we'll see in an example that we're going to do later. So that means at any particular given time, g of v is really just saying that, hey guys, this is the length of the shortest path that we have found so far. Okay, there's no guarantee that that actually is the length of the shortest path, but of all the paths that we have explored up to this point to this particular vertex v, this is the best we have got. All right, next we have Jonathan asking, why not just set GV and FV to infinity? That's what we are doing. That's what we're doing in the algorithm, except for one specific vertex. Okay, let me double check, because just in case I did something stupid when I typed the notes. Oh, this is not multiplication. This is actually just the first part. The second part is comment. So if you look at this here, that's actually the divider of how we assign a value to g of v, and then it explains what g of v is about. There we go. Okay, I do apologize. It's not clear. That is the second part are basically comments. Yeah, use slash slash or pound sign. Depending on which programming language we're dealing with. With Python, you use a pound sign. With everything else, just about, we use slash slash. There we go. Okay. So let me see if I can fix the notes a little bit so that it's not as confusing, because I did not think about that. I mean, you guys can locate issues that I do not think about at all, which is good. Not for me, but it's good. It's a good thing that you guys can think about it, can look at this and go like, hey, how are we supposed to interpret that? Okay, so this is 0310, and we are looking for the A star algorithm, and then the explanation of the initialization is where we are having the issue. So that would be right here. And alright, so I can do a slash slash, I can use a colon, I can use a pound sign, or I can just say explanation colon. There we go. I think that should be clear enough, hopefully. So we'll go ahead and put one over here too, explanation. And let me see if I have anything like that later on. Probably not. Okay, there we go. So I'm gonna republish this particular module. There we go. Alright, so Control Shift R, refresh the whole screen, and now it's a little bit better. See, yeah, we got explanation colon. Oh, okay, this one is plural when it's not supposed to. Darn it. There we go. Just fix the grammar. There we go. Do it one more time. Alright, so now we should be good. Alright, cool. So that problem is now fixed. But thank you for pointing it out, because because I wrote the notes, because I got the concept in my head already. So when I read my own notes, it's like it makes perfect sense. I don't see a problem with where's the multiplication. Yeah, but if I did not know about these concepts before, yeah, that can be confusing. There we go. Excellent. So are we better? Are we good now? In terms of what G is representing and what F is representing. All right, very good. So we initialize G of V and F of V to infinity for all of the vertices except for one, except for the start vertex. So for the start vertex, we initialize G of V if V is S. Okay, if variable v is variable s, then we initialize G of v to 0, and we initialize f of v to the heuristic value between s, which is the starting vertex, to x, which is the destination vertex. Does that make sense to you? Okay, so let's switch back to the graph, okay, to the picture. And does that make sense to you that my initial estimate between S and X is going to be just h of Sx? Exactly. So Jonathan is absolutely correct because the starting point is 0 distance away from itself. So that means g of s is going to be 0 because g of s is trying to figure out how far are we from the start vertex. So the question is now saying, how far is the start vertex from the start vertex itself. So it kind of makes sense that that's just going to be 0. So the next question is, what is the estimate between the start vertex to the destination vertex? Oh, we just kind of pull that x value between s and x and we're done. Exactly. So Aman is correct as well. It is just the heuristic value in that case. And that is why in the algorithm, we initialize the g and the f value of the start vertex to be just 0 and the heuristic function applied to s and x. So are we okay so far with this initialization? The next one is a little bit cryptic, okay, because we have a pref function. So the pref function is basically just asking, in order to get to a particular vertex, how should I get there? So it's keeping track of back pointers. So if you think about a singly linked list, this is basically just a pointer to say, oh, I got here because I came from blah. Okay, I came from that vertex over there. So before we explore before we explore the graph, in any way, all we can assume is I really don't know how I got here because I don't even know whether vertex v is reachable from the start vertex or not. Okay, and the start vertex itself also has a undefined for pref because why would I care how I got to the start vertex? By definition, this is where we start. I don't really care that it should be undefined how I got to the start vertex. So that's why it doesn't matter which vertex we are talking about in V. We initialize every single previous or back pointer for the vertices to undefined. So that's why we have this thing here. And pref is basically how we will represent the solution when we run the A star algorithm. There's no E prime in the A star algorithm. There's only back pointers to the edges, to the vertices. So when we're all done, hopefully, when we're all done, we will see that the destination vertex X is going to have a pref, and then the previous of the destination vertex, hopefully that will also have a pref, and that one hopefully also has a pref, and so on. So we can track all the pref all the way back to the start vertex, and now we have found the shortest path. So when we're all done with this algorithm, we basically track the back pointers starting from the destination vertex in order to identify the actual shortest path. So are we doing okay in terms of just understanding what is what? Because there are a lot of things here. So we have V, uppercase E, we have lowercase d, we have lowercase s, lowercase x, lowercase h, lowercase g, lowercase f, and then the pref function. We have all of these things to track when we run the A star algorithm. Yes, so pref of v is a vertex. In some way, okay, so let me go to Joplin first because I want to type this out. So if we want to identify what is the pref function, what is it, right? So that's one question that I want to answer. So if we look at the pref function, okay, and math rm pref, okay, the reason why I use math rm is because I don't want it to be in italic. I want this to be just in regular text. So if I want to look at pref as a function, so we have a colon. The question is, what is the domain and what is the codomain? That is the question. So what is this question mark over here and what is the question mark over here? I'm going to let you guys think about this a little bit because it seems obvious, but it's not. That's a good starting point. Okay, so I think what Jonathan meant is actually this, right? You are mapping from a vertex to a vertex because you're trying to find the previous of a particular vertex, which is also a vertex. So I think that's what Jonathan meant to say. But there's one little problem with this approach. It's very close, but not quite exactly what we want. Now, it's not about the Cartesian product. It is about the initial value, the initial way of how we map each vertex to. Because we map it to undefined, and undefined is not in the set of vertices. There's no such thing as an undefined vertex in the set of vertices. Not a difference. We just need to. Okay, so right now, the way we assign things into this function makes it not a function. Okay, this, or I should say, this does not describe it as a function. So what we need is to change the codomain, and we're going to use cup, which is the union operator, and we are just going to add a specific value which is called undefined. So I'm going to use math TT in this case. Hopefully that exists. Looks like it does, and we'll call it undefined. There we go. Because the codomain needs to have that one extra value so that we can initialize the function to begin with. What does undefined mean math-wise? It has no meaning. In other words, if you ask your professor, your math professor, and say, what is undefined as a particular value that we want to put into a set, your math professor would look at it and go like, that doesn't make sense. Your entire question makes no sense whatsoever. In programming, on the other hand, and this is why I chose to use TT as a font for undefined. I believe TT is the abbreviation of teletype. I could be wrong, but I think it's teletype. It makes it look like what program text, right? Because it's basically Courier in this case, and that's because in some programming languages there is such a value called undefined. JavaScript is one of those languages that actually has a value called undefined. You can actually compare the value of a variable to the constant of undefined. Now, undefined is actually a little bit more than just that. Okay, undefined actually has a type, and it actually has a type of object in JavaScript. But I'm not going to get into JavaScript programming here. All I'm trying to say is we need this one extra element in the codomain because during the initialization, we need that. Okay. Now, as the algorithm runs, okay, some of the vertices will no longer map to undefined because we have found that, oh, by the way, in order to get to this particular vertex, we can go from that vertex to this vertex. Okay, but initially, because of the way we initialize the function, technically speaking, in order to make prev an actual function, we need undefined as one of the elements of the codomain. So we're exactly because that's what the union does, right? Because the union between v, okay, fine, I'm gonna put some extra parentheses to make it clear. Okay, so we are putting the open paren here and putting the close paren over here. There we go. Oh, by the way, for those of you who are not taking CISP440 because you would have seen me doing that yesterday already, Joplin actually has a, okay, let me see if I can show you that. I know I'm digressing a little bit here, but this is actually kind of exciting to me, so I'm going to show you. So if you go to, I think it's appearance. I could be wrong. Let me see, check. Nope, it might be just general. And right here, you can see in keyboard mode, it has Emacs, Vim, and default. Default is basically, for those of you who like to use Microsoft Word, Notepad, and Notepad++, all the usual editors, the default is for you. And Emacs is basically a rival of Vim or VI, since the really early days. The quickest way in order to start a holy war between older programmers is to ask them, so what is the best editor? Is it Emacs or is it Vim? Yeah, and then you just have to kind of step back and watch the fireworks, because that can spark pretty nasty comments and nasty conversation between programmers. All right, so there we go. Anyway, are we okay so far? The way I define prev as a function, the domain is still just all the vertices, but the codomain needs to include the undefined value, because that's how we do all the initialization. Okay. All right. So cool. Yep. Some people do that Emacs with Vim binding, and you cannot do the reverse, unfortunately, because Vim has that very distinct edit mode versus navigation mode. So yeah, some people call Emacs an entire operating system all by itself. All right, so now we're getting into the actual algorithm itself. So instead of using instead of using Q, we have uppercase O, which serves about the same purpose. In other words, the set O is representing all the quote-unquote boundary vertices. Okay, the boundary vertices being vertices that just got their G value updated. Okay, so that's what the set O is representing. It's kind of the same thing as Q, but the reason I do not use the term Q in this case is to avoid the confusion. Because if I were to use exactly the same variable name, then people can potentially misunderstand which one we are talking about. So by naming this particular set O, hopefully that those confusion can be avoided. And this is how we initialize the set O. Instead of using the set of all the destination vertices, like the way we did it on Monday for Dijkstra's algorithm, we initialize this one with the single start vertex that we have. Okay, and now we are into the actual algorithm itself. I'm looking at the time. We might be able to get started with a trace today. We may not. So we'll see how it goes today. So when we look at the algorithm, you can see that, so the way we stay in the loop is different compared to the one before. The one before, we just say, okay, as long as Q is non-empty, we'll keep going. Okay. Now that might actually be a quicker way to exit the loop, and I will kind of think about it. But in this case, we definitely do not have the same thing. So let's find out what is the condition to stay in the loop. In order to stay in the loop, this is the condition. There exists v, lowercase v, which is an element of the set O, such that f of v is less than g of x. Okay, so let's think about all of these terms first. Okay, so v itself is really just a local variable that is bound to at least one element of O that can satisfy this requirement. So all we are trying to say is, in order to stay in the algorithm, we need to be able to find at least one vertex in O such that f of v is less than g of x. Oh man, that's abstract, right? I mean, f of v is less than g of x. What the heck does that mean? Well, let's find out. F of v is an estimate. Okay, it is an estimated length of the shortest path from the start vertex through vertex v to the destination. In other words, it is an estimate of an entire path from the starting point to the destination through a particular vertex. What is g of x? I'm gonna have you guys answer that question. What is g of x? the actual length of what? So far it's right. Okay, so that is correct. Okay, so weight is correct. G of x is the length of the shortest known path from the start vertex to the destination. It doesn't mean that's going to be the actual length of the shortest path. It simply means it is the length of the shortest path found at this particular point in time. So what does it mean if f of v is what does it mean if this is not true? Okay, if uppercase O is not empty, but for all the vertices in uppercase O, f of v is greater than or equal to g of x. What does that mean? Remember, f of v is basically g of v plus h of vx, right? Because it is it's the length of the shortest known path up to this point plus the estimate to the actual destination. So what if all of the f of v are greater than or equal to g of x? What would that mean to you? And we know the h values are underestimates. Correct. So Jonathan W is correct that if this is true, okay, if I can find at least one vertex in O such that f of v is less than g of x, that gives me hope that I might find a shorter path than the one that I have found so far. Because g of x is exact. Remember, g of x is the exact length of the shortest known path up to this point, okay? And then f of v is an estimate. F of v is an estimate of the shortest path from the starting point to some vertex v, and then the estimate from vertex v to the destination. So if f of v is less than g of x, that means there is a potential, not always, right? I mean, there's no guarantee, but there's a potential shorter path to the destination vertex. But the other way to look at this is exactly the opposite. What if the f value of all the vertices in O are greater than or equal to g of x? And because the heuristic function is an underestimate, so that means the actual length of all the paths going through every single one. Okay, let me see how I can put this correctly. So for each vertex in O, if I look at a path from the start vertex through that particular vertex to the destination, the actual path is going to be greater than or equal to g of x also, which basically means I cannot find a shorter path anymore. Does that make sense? And that's why this condition has to be true in order for me to continue the loop. I mean, I don't need to, but if I use the same condition as in Dijkstra's algorithm, and basically until the set O is empty, I'll be doing some iterations that is unnecessary, because at a certain point I already know I cannot find a shorter path anymore. So any further processing is really just wasting cycles. All right, so we got. Oh, sorry, I forgot to read the text channel, so I really don't know what Jonathan is referring, what that is referring to in Jonathan's first text comment. How does this handle when there are no paths to the destination? That's a very interesting question, right? So if there are no paths to the destination from the start vertex, right? So the start vertex, would go places, right? It would go places. It would basically explore every single vertex that is ever reachable to the start vertex, and then it will find out that, oh, okay, there's no way to proceed. So in that case, the destination vertex won't even be in O anymore, because in order for a vertex to end up in the set O, it means that vertex needs to have its g value adjusted to be non-infinity. So the loop will still exit. It's just that the destination vertex won't have a pref. And that basically means it is unreachable. Does that make sense? Okay, what the condition means again when it's true. Okay, so when this condition is true, that means there is hope that we might find a shorter path from the start vertex through vertex v to the destination, but there's no guarantee that that's going to be the case. It's just that there is a potential that we might find a shorter path. And that's why even if the destination is not reachable, even though it is actually not connected to the start vertex, this algorithm will still complete. It will still come to the correct solution that the destination is not reachable, but it will only get to that conclusion after the start vertex, after the algorithm has looked into every single vertex in the graph that are indeed reachable from the start vertex. All right. Cool. At this point, I'm pretty sure we won't have enough time to actually go through an example, but I'm going to go through the logic of this code, at least explain what each one is trying to do. So this way, you can, if you want to. Well, okay, I'll rephrase that. Not if you want to. I'll qualify what you want to. If you want to get a good score out of the final exam, you probably want to do this. Okay, you probably want to take what I have here. Okay, I'll publish this as a PDF at the end of the class. Not a problem. So you will actually have all the starting points that you need in order to basically try out the algorithm, to trace it on your own, and then on Monday we can talk about the solution. Okay, so it is very important to do this over the weekend, especially because this is there will be 5 days in between. All right, so let's get started here. So just like the Dijkstra's algorithm tries to select a vertex out of O, based on a greedy or optimistic view, we are going to do the same thing over here. So what we are doing here is for all vertices in O, we want to find the one that has the least f value. So in Dijkstra's algorithm, we're trying to find the one that has the least L value, but in this case we're trying to find the one with the lowest or the least f value, because what the f value is representing is an estimate. It is an estimate of the length of the shortest path from the starting point through whatever vertex we are talking about here to the destination. In other words, we're looking for the most optimistic option of all the options available. Okay, so that's basically why we select this the C using this particular way. Once we have selected a particular vertex to expand, then we're going to remove it from the set O. Okay, just so that otherwise we can get into an infinite loop situation. And then this time, instead of looking at all the incoming edges to the vertex that we have selected, we're looking at all the outgoing vertices from the vertex that we have chosen. So instead of looking at all the incoming arrows to the vertex, we're now looking at all the outgoing arrows from the vertex that we have chosen. So this n here is a local variable, because it is it's the destination of the edge going from C, which is chosen from the first step, to on that particular edge that we're considering. The next step we do is very similar to what we were doing in Dijkstra's algorithm, except this time we have to take into consideration of the heuristic function. So the first one is, in this case, I use a temporary variable, just to add g of c and d of cn. So when you look at g of c and d of cn, that becomes potentially the new g of n. Okay, because g of c is the length of the shortest known path from the start vertex to vertex C. We know there's an edge going from C to N, so when we add the distance from C to N, then we end up with a potentially new g of n, because g of n is the length of the shortest known path from the start vertex to vertex n. Okay, so this is it has a lot of parallel compared to what we did in Dijkstra's algorithm. So now the question is, did we actually find a shorter path? If we did, okay, if we did find a shorter path from the start vertex to vertex n, okay, which is when this particular condition is true, then we do something very similar to what we did in Dijkstra's algorithm. The first thing we did was, well, okay, the ordering does not matter in this case, but we are eventually going to update g of n to be t, because that's the length of the new shorter path from the start vertex to vertex n. And because of that, we're going to add n into the set of O, because now we are saying, oh, guess what? We just updated the g value of n, which basically potentially can mean all the outgoing edges of n can also result in shorter paths, to the vertices that n can touch. So that's why O is getting a union with vertex n in its own set. We also want to update all the f values. So technically speaking, you don't have to store the f values, okay? Because all the f values are basically the g values plus each of whatever the vertex is to the destination. So technically speaking, you don't have to represent the f value by themselves and always rely on just g of n plus h of nx. But that also means when you do the computation here to try to find the minimum of all of the f values, you're going to have to go through a lot of repetitive computation. So might as well just store those values so that you don't have to repetitively compute those values over and over again. So that's why your f value is stored instead of just computed on the fly when we go through the algorithm. Our time is almost up. Just one more thing to do here. So the very last thing we do is to keep track of how do we get to vertex n, okay? Because we just found a shorter path from the start vertex to vertex n. We better remember how we got there, okay? Because this path can potentially be the one that will lead us all the way to the destination vertex. So this is why we also have to update the prev value of n and say that, oh, guess what? We found a shorter path from the start vertex to vertex n through vertex c. So that's why we now have to remember the previous of n is c itself. So when we are done, when this while loop exits, then we can define GSX. I use this notation simply to mean this is the solution graph. Okay, the solution graph is going to have exactly the same vertices, and then ESX is basically a set that I'm constructing on the fly. I am using all the prefs to construct E of Sx, but you can basically just start with the destination vertex and then start with that and go backwards until you get back to the start vertex, because it's going to be one single path from the start vertex to the destination vertex. It's the rest, the other edges are basically useless, but if you follow this logic here, those would also be represented in ESX, but they won't be of any use to us. Alright, so our time is up. So this is your ungraded assignment over the weekend, is to track the A star algorithm based on this particular input. And I think I'm going to give you an actual graded assignment using Dijkstra's algorithm. Obviously, it's not going to be based on this graph because we just solved that on Monday, but I'll give you a graded assignment as well. So now you have two things to do over the weekend. One is graded because it is based on Dijkstra's algorithm that we have talked about. The other one is ungraded because it is based on the A star algorithm that I have described, but I haven't traced it yet in class. Okay, so Wade has one item in the text channel. What would we call the subset of V within O which are not currently in G of V's range image? I'm not exactly sure what that means. Let me switch back to the algorithm first. Okay, so this V is the one that you're talking about. How do we call the subset of V? V is not a set, so it cannot have a subset. I'm guessing you mean the subset of O, where each element is not in G of V's range. Subset of O containing V. Okay. I'm still not really sure about G of V's range. The values actually used by the function. Which function are we talking about? G as a function? Now remember, G of V is just a real number. It has to be a non-negative real number. So it is not a set of vertices. It would be a set of numbers. I mean, the codomain of G is the set of all the non-negative real numbers. I think I understand what Wade is trying to say. Basically, we have a whole bunch of vertices where the G values are less than the G value of G of V. Is that kind of what you're implying?
I forgot that I could speak. Um,
Go ahead.
yeah, so when we're first starting off, right,
Mm-hmm.
the distance, the sort of the set of real numbers
Mm-hmm.
represented by G of V is like null. There's nothing in there because we don't actually have a distance between an actually known distance between the 2 points. It's zero or infinite, right?
Right, except for the start vertex. Yep.
Yeah, except for the start. Yeah. So um, as we explore, that changes. The set containing all vertices in the domain, containing all the vertices within the domain that map to real values of distances, right? So all of the past distances that we've passed.
So some of the G values will go from infinity to some actual non-negative
Yes.
real number. Yes.
Yeah.
Yep, that is correct.
Um, and then, but so the numbers being fed into the function of all possible v, um, that decreases, right? All possible v that could have a shorter path than the current what's currently held, and decreases as we increment the program until the point where there is no value held within that set that could be fed into f that could give us a smaller real value than anything that's currently defined within the domain of G.
Hmm. Would it be fair that you're asking about the vertices in O? Okay, so let me scroll back to
Yeah.
the A star algorithm. So would it be fair that you're actually asking about the vertices in O where the f value are greater than or equal to the g value of x? What are we going to do with those vertices that are in O at this point of time, at any particular point of time? Is that
Kind of not necessarily greater because G is at one point max length, right? It's like
what
infinite.
Well, g of x was initialized to be infinity, so
Yeah.
the first time g of x becomes a non-infinity
Yeah.
number has to be because of this line over here, which basically means we found a path from the start vertex to the destination vertex. That's so when g of x is not infinity anymore. That means we have found at least one path from the
Okay.
start vertex to the destination vertex.
Yeah.
But that path, the first one we find is not necessarily the shortest one. And in order to determine whether there will be a shorter path or whether it is possible that there's a shorter path, we have to compare g of x, which is the length of the path found at this point, to the potential to the estimate of paths going
Yeah.
through other vertices
Mhm.
to the destination vertex.
Yes. So yes. So I think that is what I am kind of getting at.
Mm-hmm.
But like if we're thinking about it during runtime as a set of values of vertices that is decreasing in relation, like so within O, right? So a subset of this
Mm-hmm.
You know what I mean? I don't know. Um,
Well, as we go through the algorithm, you will find the g values potentially to be they're always decreasing because of the way we set up the conditional statement. So you can see that we update a g value only because we found a shorter one. We found a smaller g value. So if you keep track of the g value, they are always as we update the g values, we are always updating the g value to be a value that is smaller than what it was before. And because the f value is the g value plus the heuristic value, so the when the g value decreases, the f value will decrease at exactly for the same amount. So you will find those values decreasing over time. The question is whether a potential shorter path becomes the actual shortest path. In other words, does it get to x, and when it get to x it is still shorter, then we have to update g of x, which basically means we have just found a shorter path to from the start vertex to the destination vertex. So we cannot throw anything out um, until we have this condition being false. Then we can basically say there's no way that we can find a shorter path anymore.
so is there a specific word for that um set that shrinks until there is no possible, you know what I mean? Like of
Mm,
possible vertexes that you know.
none, yeah, none that I'm aware of. Um,
Okay, that was the main question.
okay, there is
Yeah.
a there is an alternative A star algorithm, and that one relies on the heuristic function having um, a different an additional property. So in addition to being admissible, which means the heuristic function cannot overestimate, it also states that the heuristic function has to be um, what is the term for that? It has to be for the I cannot remember the exact term, but it's basically it has to be unidirectional. In other words, it has the feel of transitive in it. If you are looking at the heuristic function of a vertex that is further away along a path from another vertex, then the heuristic function of the one that is actually further, the heuristic value of that one cannot be less than the heuristic function of a vertex that is actually closer to the destination. So if you add that additional property to the heuristic function, I think the algorithm can be adjusted a little bit. And if I remember correctly, I cannot be 100% sure. If I remember correctly, there's another algorithm, and another A star algorithm that tracks two sets instead of one, and the other set, would be the potential candidates. But I have to look it up to confirm that.
Yeah, because that's exactly um, that's kind of that pretty much is exactly what I was thinking of, was just um, that there must be some set out there of values that could possibly lead to a shorter path, and having that extra constriction would define that.
Mm. Well, right here, using the existing algorithm, that's what O is. The set O is basically every single element of O is a vertex that has just gotten its G value updated to be something smaller than before.
Mm.
So the
Yeah.
idea of tracking these particular vertices is if a vertex, that has other vertices, that it can go to, it has outgoing edges. So if a vertex, is just updated, its G value just updated, and it has outgoing edges. So that means, the vertices connected by the outgoing edges of the one that just got the G value updated, those can potentially have found a shorter path as well. And that's why, those other vertices are added to O using this union operation here, because because they are reachable from a vertex where we just found a shorter path to. Is that it's the
Yeah,
same
yeah.
mechanism. It's the same mechanism as Dijkstra's algorithm, except this one goes forward instead of backwards.
Each neighbor n within V such that C. Yes. Yeah. Yeah. Okay. Thank you.
Sure.
All right. Thank you. That was helpful.
Oh, okay, sure. Yeah, absolutely. And Jonathan is correct too. We only have one start and one end in the A star algorithm. The A star algorithm cannot solve for all shortest paths from all vertices to a destination. So, so there are nuances, between the differences between the two algorithms. Um, yeah, so I think if you guys try to apply the A star algorithm, using the problem set that I have here. This is nice because I'm using exactly the same distances as in the one in on Monday, and we can assume A is the start and then E is the end. So let me just kind of add that here. And that will be the end of today's lecture. E is the destination, and then A is the starting point. So with this, you guys have everything that you need in order to basically give the A star algorithm a try. Okay, just to find out, okay, what do we do here? Um, I know we are running out of time, but I'm going to add this part too. So the A star algorithm has a cousin called the C star algorithm. So the question is, what if you have a really large graph and things are very complicated and you don't have enough time to figure out all the way to the actual solution? So that is the interesting part, about these algorithms. It's like, okay, what if we don't have enough time? What if you are a robot trying to decide what to do and you have a hard real-time requirement constraint of you have to do something before this time expires? So the C star algorithm is kind of like the A star algorithm, but applied in a what we call a successive recursive manner, and that one gives you a suggestion of what you can do next, even if you cannot explore all the way to find the actual shortest path to the destination. But it's only doable because we have the heuristic function helping us to guide us to, okay, which point should I go at this point, and which one should I go at this point. So that's it. Okay, that's the end of today's lecture. I promise. So I'm gonna get out of the voice chat and stop the recording. I see most of the class is gone already.